we talked about the birth of stars. We talked about the life of stars. Now we're getting into the death of stars. So here's a picture that shows, it's just a starting picture. I didn't even worry about titling it. Shows a star dying, and down here are molecular clouds that stars could then form in. Stars tend to recycle matter. The original stars would have been made primarily of hydrogen and helium. But if you have a star in the vicinity that has died, then during the death of stars, you can make elements that are bigger than hydrogen and helium. For instance, our sun right now is making helium, but what is our sun going to ultimately make? What happens when the sun runs out of hydrogen in its core? It starts, first it'll have the hydrogen shell that starts fusing outward, and then it will start fusing helium in the core. And the fusing helium, I told you I was going to, well, it actually doesn't take much. 3 helium nuclei produces a carbon nucleus. We don't need to show anything else. That's basically the process. 3 helium nuclei have to come together at once to form a carbon nucleus. And so it's called the triple alpha process. So our sun is going to do that. It will also make some oxygen. How do you suppose it's going to make oxygen? A helium plus a carbon will make an oxygen. So our sun will produce helium. Well, it's producing helium right now. When it's in its death throes, it will produce carbon, and it will produce some oxygen. And then it's going to have no more. It will run out of fuel. It can't reach the temperature and pressure necessary to cause fusion of the carbon and oxygen. So it'll just be done. So here are final stages for stars of different sizes. Less than 0.01 solar masses, it's a planet, it's not a star. So it's not going to end up as a star. If it's between 0.01 solar masses and 0.08 solar masses, it will end up as a brown dwarf. And this takes a little bit of explanation. We talked about our sun. At the exterior of the sun, how does energy get out? We had 2 mechanisms for energy transportation of the sun. What was the one at the exterior? We had the granules on the surface, and you had a test question about those granules. Well, it said, how do we know we have this mechanism? So we talked about in class today, folks. The 3 of you.
What? Ask that again? Sorry, what?
That we talked about in class today. We talked about 3 mechanisms.
Convection.
Yeah, convection. The surface has granules that are direct evidence of the convective currents. And when you have convection, you have material transporting the heat, the actual, what's the primary makeup of the sun? Element is hydrogen. So you have the actual hydrogen moving in circles like this. So the hydrogen in the exterior of the sun is cycling around. Inside, we have the radiative zone. Then it's electromagnetic radiation, and the hydrogen is not really moving much. So you don't have much mixing. So as the core is doing fusion, the hydrogen in the core runs out, but you still have hydrogen outside of the core that can go on with fusion. And then when you have the fusion shell of hydrogen, you dump more helium into the core. Well, if you have a smaller star, that convective region gets closer to the core. And so if you get down to 0.08 solar masses, the star will have complete convective mixing. So you're mixing material from the entire star into the core and back out. What that means is when the core runs out of hydrogen, the whole star is out of hydrogen. And so that's the case there with the brown dwarfs. You have the whole star runs out of hydrogen, starts collapsing, and it it can't reach a temperature to fuse helium, it just is going to fade away. So brown dwarf is it just gets cooler, smaller, fades away. Now, has that ever happened? No. No, because the lifetimes of stars are such that no star that's that small should have ever died. There you have very long lives. Then we go from 0.08 to 0.25. They're going to make white dwarfs. So we have to learn about white dwarfs. So that's our first order of business. That's what the next slide after this starting is talking about white dwarfs. So we have white dwarfs made of mostly helium for stars from 0.08 up to a quarter of the mass of the sun. If it's a quarter mass of the sun up to, notice it says 8 solar masses, it'll become a white dwarf made up of mostly carbon and oxygen. That's where our sun is. It will be a white dwarf, carbon and oxygen. We'll learn something interesting about that 8. It has to be less than 1.4 solar masses at death. 8 solar masses at living, 1.4 solar masses at death. They blow away lots of their mass in their death throes. Then 8 to 10 solar masses, white dwarf made of oxygen, neon, and magnesium. That's something that was able to fuse a little higher, but still ends up with less than 1.4 solar masses. 10 to 40 solar masses, then we have a supernova explosion. Then we have the star blow up, and what it leaves behind is a neutron star. So we'll have to learn about neutron stars today as well. And then if it's more than 40 solar masses, kablooey, and it leaves behind nothing but a black hole. I say nothing but a black hole. Once again, we have to learn more. That's not going to be today. Actually, we won't get into neutron stars. We'll just talk about what they are. And we won't talk about black holes at all today. That'll be for Wednesday. So let's get started. The death of a sun-like star. Now, I always like to make sure we remember the process. So let's start from birth to death. Where on this HR diagram was the sun when it was born? Before it became a star, when it was just a twinkle in the molecular cloud's eye. Yeah, it'd be way out here because it's really cool and giving off no light. And then as material starts being collected, what happens? It gets brighter and it gets brighter and it gets hotter. Can't see it though, right? Can't see it because it's covered by a cloud. Then it comes on down to the main sequence, and then it spends 90% of its life on the main sequence. What's its path on the main sequence look like? Something like this for its main sequence life. And then we have the death. So in death, it's going to come up like this, come down, have a little stability, come up like this again. And then we get to where we are now. So in death, what was going on when you had it going up dramatically, getting cooler and a lot brighter? It's getting bigger. It's getting redder. So it's going to be a red giant, right? And what makes it a red giant? The what?
I was just going to say, isn't that the area where the red giants are categorized or whatever?
Yes. But what makes it? What's going on in the star to make it a red giant? Okay, you have the core is pretty dormant, but you have the shell burning outward. Those two things are what's making that. Then we had at the top here a thing called the helium flash. What made the helium flash? Not when it runs out of hydrogen. That's when helium, if you have a star that reached degeneracy in its core before helium started fusion, then you'll have all of the helium has the conditions for fusion at the same time, and it all starts fusing at once. And so you have a big explosion. So that's what causes the helium flash. Then this little region here is actually a second main sequence. That's where you had stable helium fusion going on in the core. And then you had the helium shell flash when it comes up here. Then you're done. Right, for our star, that's the end. Once the helium shell is over, that's all she wrote. And so what's going on after that is going to be the death throes. So something the size of our sun is just on the cusp of making a planetary nebula. Some people, I don't recall seeing it in our textbook. Some people believe our sun will make a planetary nebula, some believe it won't. It's just right there where they're not sure. But what is a planetary nebula? It's called planetary because you have colors like the colors of Neptune and Uranus, blues and greens, pretty colors. A planetary nebula is produced when you have all of this gas that the star has been exhausting in its death stages. Right? When it has all of that expansion, it's also blowing stuff off that's never coming back. So you have a big cloud surrounding the star from its death stages. And then when it actually dies and collapses, it sends a shock wave out into that cloud. And as the shock wave hits material, it excites it and makes it so it gives off light. And so the planetary nebula, you have a ring, and you have material giving off light because of the energy that's been deposited by the shock wave. So it's pretty cool. And then she fades away, just fades away, and ends up, so it comes down like this, ends up down here as a white dwarf. So you notice here, it talks about what's going on in specific stages. As a giant, again, a second time being a giant, point A. It will lose more and more mass as its core begins to collapse. It gets hotter and hotter, okay. So this is core collapse going on in B. And then, yeah, and then it's just cooling off, moving down to C. How big is a white dwarf? I already forgot his first name. Chandrasekhar. He was the person who realized something really funny about white dwarfs. White dwarfs are held up by what we call electron degeneracy. I know I mentioned this in class on Friday, but you have, in a star, everything has the electrons stripped away. So you don't have an electron with a proton. Hydrogen is just a proton. Helium is 2 protons, 2 neutrons, no electrons. And then you have the electrons. And quantum physics says that no 2 particles that are indistinguishable can share the same space. So there's something that keeps electrons from sharing the same space, keeps pushing them apart. And so degeneracy is what we call it when you have everything as close as you can get. Actually, yeah. Degeneracy is more than one particle of the same energy state. You can't have degeneracy, so it's the fact that you can't have degeneracy that's keeping things from coming too close together. And so it holds the star up. As you put in more mass, it actually shrinks a little, because as you put in more mass, the gravity becomes stronger, and it slowly is pushing things together, fighting against that degeneracy. Until if you get enough pressure, you'll actually force electrons to go into the nucleus of an atom. And when you force the electron to go into the nucleus of an atom, then you have interesting things occur. And so the Chandrasekhar limit, that's, you can see there, just under 1.4 solar masses. Let me hide this thing here that says that we're sharing right now. Whoops. The Chandrasekhar limit, I hope I'm pronouncing this right. Satish told me that it was something like that. I'm trying to say it right. I used to say it differently. Anyway, so this limit is the limit where you have enough force to push electrons into the nucleus. You push the electrons into the nucleus, the whole thing blows up. And it's what we call a type 1a supernova. So if you get a white dwarf that's up to that big, it will collapse and blow up. And we will talk about those just a little bit at the end of the lecture. So white dwarfs have to have a mass that's roughly 1.4 solar masses or less. So on that chart it said that stars as big as 8 to 10 solar masses would end up as a white dwarf. Well, they have to be less than 1.4 solar masses at their death, or they're not going to be a white dwarf. So what is a white dwarf then? I've said it's held up by what? Electron degeneracy. For the small mass white dwarfs, ones that are less than a quarter solar mass, you never had enough mass to make fusion of helium occur, and so it's helium white dwarf. Helium is packed very tightly. If it's a star the size of our sun, up to 8 solar masses even, it's going to end up as carbon and oxygen, so it's carbon and oxygen white dwarf. Something 8 to 10 solar masses will have, things like silicon, magnesium mixed in there as well. It's still white dwarf, held up by electron degeneracy. What's the size of a white dwarf? Maybe about the size of the Earth. So, you think about that, you take something the size of the sun, you compress it down to something the size of the Earth, that's pretty dense. Here's a picture of Sirius A. And it has a companion, which you can just barely see in the picture on your right. There's its companion. This is intentionally the contrast is set so it's way too much light on Sirius A, the bright star, so you can see the light from Sirius B. Now that's a binary star. Two stars that form together and are orbiting each other. Except for one is a white dwarf. What does that tell you about the white dwarf?
That means its mass was less than.
At death, its mass was less than 1.4 solar masses. But it's already dead and its companion's not. What does that tell you?
That it was a smaller star.
Otherwise, bigger. More massive stars burn out quicker. So that was the more massive star. Now, in this situation, you can have something interesting occur. When Sirius A is in its dying stages, it will be blowing off mass. Some of that mass will funnel on over to Sirius B. And so Sirius B will start gaining mass at the expense of Sirius A. And as Sirius B starts gaining mass, well, you can actually have it kind of rekindle a little bit. But what's more likely to happen is you just get more hydrogen gas on the surface of that white dwarf until you reach a high enough pressure on the surface for fusion to occur. And you'll have fusion occur on the surface of the white dwarf. And so all of a sudden the white dwarf will flare up really bright, and then all that hydrogen is turned into helium and it falls back down on the surface. The white dwarf doesn't even care, and it was all exterior. And it just gained a little mass. We call that process a nova. Nova being Latin for new. Why new? Because it looked like a new star for at least a short period of time. If that occurs enough times, the star's mass will increase until if it reaches 1.4 solar masses, then the whole thing will collapse. We'll have a type 1a supernova. All right, so let's move on. Massive stars. Massive stars are going to fuse all the way up to iron. Why do they stop at iron? Does anyone remember why they stop at iron?
It's just like ash.
It's the most stable.
Oh, yeah,
It's the most stable nucleus. Yes, we call it ash, but it's the most stable. We call helium ash, but helium can be fused further, but the iron can't. The iron, if you force it to fuse, it's going to, our book, it's kind of goofy, I think, the way our book talks about it. It's going to make somebody pay for it to fuse. It's what we call endothermic. It's going to require you putting energy in to make fusion occur. So you create elements all the way up to iron in these massive stars. So on Earth, we have a fair amount of iron. Where did this iron come from? On Earth, we have a fair amount of iron. Right? The Earth is primarily iron and silica. Yeah, silica and oxygen. Remember, why do we have primarily iron and silica oxygen for the Earth? In the crust of the Earth. Why is it primarily those two things? We did learn this. The Earth formed inside the frost line, in the region where the temperature was high, and so the only things that could stick together were things with high melting temperatures. And those are two things with high melting temperatures. So that's why we have primarily those, according to the scientific theory. And so the fact that the Earth has a lot of iron suggests that when the sun formed, there had been another star that had died before the sun formed. Now, the sun's believed to be about 5 billion years old. The universe about 13.8 billion years old. So there must have been a star that was large enough that its lifetime was under 8 billion years, that formed, lived, and died in our region to provide the iron and whatnot that we have for Earth. Without that, we wouldn't have a rocky planet. Now, I have to bring this up just because my wife made me watch it. We have a relative who is Muslim and sent a link about things in science that prove the Quran to be true. And it had some things that were interesting. Like, for instance, the Quran says that God put up the sky to protect us. And as we've talked about, the sky does protect us, right? The sky has the ozone layer that protects us from ultraviolet radiation, and it burns up meteorites that come into the atmosphere for the most part. So it is a protective barrier. But then it talked about iron, and the Quran says something about, you planted the iron, and it said that science says that the iron came in from asteroids. Not so. The science says that the iron was made in a previous star's death and was the primary thing, iron and silica, because of the high temperature that formed the Earth to begin with. So you win some, you lose some. What happens when this massive star runs out of fuel? When everything is turned into iron in the core? What's the core going to do when it's just iron? Okay, well, it's going to start contracting first before the collapse occurs. It's going to start contracting, and you're going to have the electron degeneracy still holding it up, as long as you still have the other shells burning out there. But when the other shells are done, which doesn't take very long, then everything comes crashing in. Things come in as fast as 1/4 of the speed of light. They're falling in so quickly. And then you have that core, and you force electrons into the nuclei, like I said, would eventually happen with the white dwarf. And when the electrons go into the nuclei, what you do is you basically reverse the whole nucleosynthesis process, the whole process of making bigger elements. The electrons are forced in there, and you take all these protons, and you undergo particle interaction with the electrons, and you create neutrons. And you have the core becomes one big collection of neutrons. It's basically a nucleus of a star, a nucleus of an atom that's about 20 kilometers in diameter, basically the size of the circumference of Lincoln, or not circumference, the diameter of Lincoln. It's the size of this now neutron star. This neutron star is no longer held up by electron degeneracy because the electrons are forced into the nucleus. Now it's held up by neutron degeneracy. The neutrons, just like electrons, quantum physics says they can't share space. And so the neutrons are holding it up by their degeneracy. And so everything's falling in, and all of a sudden the nucleus converts into just one big nucleus made of neutrons. And all of this energy that's falling in bounces off, and you have a big shock wave going out. It produces enormous amounts of neutrinos. Now you remember we talked about neutrinos. Neutrinos are these little boogers that have no charge, virtually no mass. They're flying through us all the time. Well, those neutrinos carry away enormous amounts of energy. In fact, less than, I think I got this right from the textbook, less than 0.1% of all of the energy that's leaving the star is coming out as light. The vast preponderance is going out as neutrinos. And those neutrinos tend to go through everything, except it's so compact when you have the core collapse that you actually really raise the chances of the neutrinos interacting. So neutrinos are, a lot of their energy is absorbed by the dust that was created by the star, giving it lots of energy, making a very powerful outward explosion. Question, Leslie?
I was going to say, you talk about stars collapsing, like, when I think collapsing, I just think of, like, things like falling and just getting destroyed. So collapsing, do you mean it just gets, like, small?
It's a three-dimensional collapse as it's going. It was here, and all of a sudden it's, like say you had an egg, and you're pushing on the egg in all directions, and then the shell breaks, and everything just comes in like that.
So yeah, it is like that. Okay. Just wanted to make sure.
But it's a collapse. It's not just it's shrinking. It's falling free fall. Okay, so here's some pictures of type 2 supernovae. That AE is pronounced E. That's the plural of supernova. Type 2 is when you have a massive star collapse. And so you have two pictures. I believe each one's 5 years separated. No, it doesn't say 5 years. Okay. But you have a time gap between the pictures, so that's why you see something different here. And yeah, the arrows are pointing to the object that you have after the supernova. The results of these type 2 supernovae are a neutron star. That object that's held up by neutron degeneracy is basically neutrons. Now let's talk about both the white dwarf and the neutron star. You have something like our sun. Our sun is rotating, right? And it goes from being the size of the sun to the size of the earth. Everything falls in. What happens to the rotation? It goes faster. What do you suppose is going to happen to the temperature? It's going to go up. So these white dwarfs are going to spin pretty fast, and they're going to be really hot, hotter than the sun, because you have all of that energy from it collapsing. So they're white because they're really hot. They're small, so we call them dwarfs. And if it's small, remember the luminosity had to do with the area, the surface area. So if it has a small surface area, what does that tell you about the luminosity? Okay, so it has a low luminosity but a high temperature, hence its position on the HR diagram. Going back to the picture on the size of a white dwarf, the white dwarfs have radii between about, well, they're roughly 10% the radius of the sun. 10%? 1%. Roughly 1% the radius of the sun. Their radii are all pretty similar. And so they're going to be on a line with constant radius, and you can determine how old the white dwarf is just by where it is on that line. If it's on the top end of the line, it's hotter, so this is going to be a young white dwarf, and this will be an old white dwarf. What's the difference in the young white dwarf and the old white dwarf?
Right.
Over a long period of time, it's going to cool down. As it continues to cool down, it will stop being bright white, become red, and eventually it'll fade away. And so they call it, when it fades away, a black dwarf. Black dwarfs don't exist yet, because the universe isn't old enough for any white dwarf to have cooled down to become a black dwarf. Here are some pictures of supernova remnants. So this here is a specific, the Kepler supernova. Supernovae have been observed a number of times. 1006, there was a supernova observed by the Chinese that was, I forgot what it is. I think they said it was something like 100 times brighter than Venus. Now think about that. 100 times brighter than Venus. They said it cast shadows at night. Wouldn't that be amazing? And so Chinese astronomers recorded this. In 1054, Chinese astronomers recorded another very bright supernova, not nearly as bright as the one they previously recorded. Then, I can't remember the date, but Tycho Brahe observed a supernova. That's what got him his fame. His Tycho's nova, which we now understand to be a supernova, was a new star he observed. And that was groundbreaking for Europe, because in Europe they had the belief that you couldn't have any change in the heavens. And here all of a sudden you have a new star that then fades out over time. And then, not to be outdone, Johannes Kepler also observed a supernova. So we have a number of supernovae. Unfortunately, there hasn't been any naked eye supernovae in the last 300 years. Now, when's a supernova going to occur? No one knows. Supernovae occur with red giants. We can look at red giants and say maybe today, maybe today. We don't know. Now, with the 1987 supernova, which is so optimistically named SN 1987A, because who knows? There could have been a second supernova in 1987. That would have been SN 1987B, right? A day before it was observed, a shower of neutrinos was detected. How many neutrinos do you suppose makes a shower? Shot in the dark. Unless you read the textbook, then it's knowledge. Huh? Okay, 1 billion. Anyone else? Okay, Vera says a small.
I don't know. They're so tiny, I'm not sure what's considered a shower. I don't know.
So Mira says a small amount. Any other ideas? Here's the thing. Neutrinos are very, very difficult to detect. So detecting efficiency is like well less than 1 in a billion. They detected a total of 19 neutrinos, which means an enormous number of actual neutrinos given their detection efficiency. And so it's called a shower because they know there must have been a huge number for us to detect that many. So they saw those neutrinos, and then a day later, the light was visible. Why the difference? Neutrinos go through most material unimpeded. So the neutrinos coming out of the core just go zipping on out. A few of them, yes, I did say there's going to be some interactions and energy absorbed, but most of them just go on out. And then they just go through vacuum space. Whee! Whereas the light takes time to get out of the star. It takes time to get out of the star because you're going to have absorption, reemission, and whatnot. So that's why the neutrinos beat the light by about a day. Even though technically the light is traveling a smidgen faster than the neutrinos. The light is traveling at the speed of light. The neutrinos are traveling at 99 point something percent speed of light. So now we have a way of actually predicting that a supernova is occurring. And by using multiple neutrino detecting stations, they can triangulate and say, we believe that there's going to be a supernova there visible within the next 3 days. And so when they see neutrino showers, they will start searching the sky to find this supernova so that they can learn more about it as it occurs. Okay, so these are pictures of the Kepler supernova remnant, the remnants of the supernova that Johannes Kepler discovered. And you have false color here, so it's broken down. You have X-rays are blue. Other X-rays are green. So blue and green are X-ray. You see a lot of blue and green there. Visible light, not much visible light there. And you can see there's some visible there, but not much. And then you have the infrared. Different wavelength ranges give you different information. And so we want to look at these. Now, if you look at the radio and the green X-ray, those to me look very similar. Of course, the green X-ray is better resolution. Why would it be better resolution? There's a good reason that you should know. Not green, but X-ray. The green is false color. But the X-rays have very short wavelengths, whereas radio waves, or infrared in this case, have much longer wavelengths. So you have better resolution with the shorter wavelengths. Even if you make a big telescope for the infrared, it's not going to be as good a resolution as a smaller telescope in the X-ray. So that's why you have more detail in the X-ray. Here is a picture of an actual supernova. Can you see that supernova right there? And this is zoomed in on it. This is from 2014. With telescopes, we can see these things that we can't see with the naked eye. So we can observe them and know what's going on. And so a supernova occurring outside of our galaxy, unfortunately. I don't think there's been a supernova in the last 300 years that we have observed in our galaxy. And the textbook says, does that mean there's been no supernova in our galaxy in 300 years? Not necessarily. It could be that a supernova occurred in a region that's blocked from us because of gas. Now, how much light does a supernova give off? I'm going to give you the answer. More light than the rest of the galaxy. And remember, the light is like less than 1/10 of the total energy coming off. Enormous amounts of energy given off when you have a supernova. Here's pictures from the Hubble Space Telescope of supernova 1987A. So there's a picture. Now this is combining information from different times, 1994, 1996, and 1997. Let me just go to the next slide. Here is a picture of 1997, that's 10 years after the supernova, and then another one, 2003. What stands out when you look at those pictures? I have to admit I'm an idiot. I looked at those and I said, well, they look about the same. Then I read the captions and I was like, oh, yeah. What stands out there? Okay. This one in 1997 has essentially a yellow ring with one bright spot. This one in 2003 has a large number, I think it says 15, of those bright spots. What's going on here to make this halo thing? What's going on is, in the death stages of a star, what is happening in the exterior of the star? Okay, you have large amounts of the exterior being blown away. And so you create a really big dust cloud. Dust is just a word here. It doesn't mean actual dust. So a really big cloud of stuff blown off of the star. And then when the star actually dies, it sends a shockwave out. And these bright spots are where the shockwave is overtaking dust and causing it to be energized. And so it says here, the hot spots are the first signs of dramatic and violent collision between the new and old material that will continue over the next few years. So it's material that was blown off in the shockwave hitting material that had been previously blown off. Over time, what do you suppose is going to happen? Right, this is only 10 years or so. What's going to happen in 100 years or 500 years?
Just fade out.
Eventually it will. That is not the slide I want next. I'll come back. Oh, okay. I apparently don't have a picture of what I wanted. I thought I had a picture of the Crab Nebula. Let's yeah, I don't think I had one today. This is the closest, but this isn't the Crab Nebula. What you're going to have is something that looks something like the pink part of this picture. You're going to have a big nebula with lots of gas, with strings all lit up because of the shock wave that's gone through all of that dust, energizing it. And then in the center, you'll have the white dwarf. Or not the white dwarf, the neutron star. Okay. Talking about just the timeline from birth to death for the star that became SN 1987A. Hydrogen fusion. How much of a star's lifetime, roughly, does it spend doing hydrogen fusion? Most of it, number-wise? 90%. 90% of its lifetime fusing hydrogen to helium. What star, what spectral class, not spectral class, what luminosity class is the star when it's fusing hydrogen to helium in its core? Main sequence. It's on the main sequence for 90% of its life, roughly. During that time, it's fusing hydrogen to helium in the nucleus. So notice there, it's about 40 million kelvins, 8 million years that it should have spent on the main sequence. Compare that to our sun. How much time do we believe our sun's going to spend on the main sequence? About 11 billion years was the most recent number I gave you. 10 billion is what we usually say. Our textbook said 11. It's probably more accurate. 10 is just an easier number to work with. So in terms of mass, is this star more or less massive than our sun? Okay, was that more or less? More. It's a little more massive than our sun because its lifetime is a little shorter than our sun. So this might have been a G0, let's say. Instead of being a G2. We are a G2. Then we have the helium fusion. 1 million years of helium fusion. So that's 1/8 as long, 12.5% if you want to be accurate, of its main sequence time, when it is now in the secondary main sequence of stable helium fusion. Then carbon fusion. Only 2,000 years. Not very long fusing carbon. 6 months neon. 1 year of oxygen. That's actually surprising to me. A couple days of silicon fusion. And look, in tenths of a second, in less than 1 second, the core collapses. Very, very rapid process. Hence the word collapse is very appropriate. It's not just a, well, let's shrink down. It's a free fall. And if you notice the temperatures in the core temperatures just keep on moving up. To fuse helium takes a very high temperature. Our sun is about 15 kelvins at the core for fusing hydrogen. That's 40 million kelvins at the core. Why is it hotter? Because it has more mass to hold up. The helium fusion, very hot, carbon, neon, oxygen, silicon. So this one here, actually, since it made oxygen, silicon, we'd say it's probably, say 3 or 4 times the mass of the sun. And you get up to 200 billion kelvins in the core. 200 billion compared to our sun at roughly 15 million. Very hot. All right, the light from a supernova. We talked about distance calibrations and the idea of a standard candle. Things that are a constant or a reproducible brightness. Do you have a question?
I was just curious where Betelgeuse is on that scale of like diffusion. Like, do we know if it's still like if it's doing it's a red giant?
Yeah, it's a red giant, so it's clearly going to be having shells burning out, and the core is no longer fusing hydrogen.
Yes.
I am sure that there is more knowledge about than what I just said, but that's the end of my knowledge about it. When you have a type 2 supernova, it's not really perfectly reproducible what's going to happen. It depends on the composition of the star. Type 1a supernovae, those are very reproducible. Type 1a supernovae is when a white dwarf reaches the Chandrasekhar limit. When it reaches the Chandrasekhar limit, we know its mass, 1.4 solar masses. We know its composition. Now, within bounds, it could be a hydrogen white dwarf. It could be a helium white dwarf. There's no hydrogen white dwarfs. A helium white dwarf or a carbon white dwarf, or it could have been one that goes up a little higher. But they're pretty similar composition. And so if it's the same mass, the same composition, and it goes kablooey, it's going to go kablooey in the same way. So type 1As are very reproducible in their brightness. The type 2s have some variation. And so that's one of the things that the scientists were really studying here was the variation in the apparent visual magnitude and the absolute visual magnitude. Of course, you get the distance, then you can get the absolute from the apparent. And so you see that over the course of the first, let's say, 50 to 100 days, it got brighter and brighter to reach its peak there. That is pretty bright. Now, remember, this is apparent visual magnitude. The brightness in the sky, would that be visible to the naked eye? Well, what would you say the apparent visual magnitude is at its brightest? Just your judgment. Just your judgment, folks. I heard a squeak of an answer. What'd you say? Okay, so about 3. Is 3 visible to the naked eye? What was our limit for visible to the naked eye? From the original standard. There were first order magnitude, second order. How far did it go down? Went down to 6. So if it's above 6, it's going to be visible to the naked eye in perfect conditions. 3 is going to be visible to the naked eye in probably any condition. Well, I shouldn't say any conditions. In San Francisco, you can see like 3 stars. Because it's way too many city lights. But in most conditions, you should see a 3. So it is something that you could see with the naked eye, actually. I said it has been 300 years. 300 years since we've had one in our solar system. This one was visible to the naked eye. It's the most recent naked eye supernova. What happens after about 100 days, though? It's fading, right? Why is it fading? Well, it's not actually a star. It's not doing something to continuously produce energy. It blew up, and now it's recovering, if you will. Now, that bump there, the textbook has as one of the goals for this chapter to understand that bump. That bump has to do with radioactive nickel that decays into cobalt And the energy from that radioactive decay causes this bump here in the brightness instead of coming down like this. So that tells us something about the composition of the star, that it had that nickel. Okay, we're out of time. We're also at the end of the slides I prepared. After this, there's slides I didn't prepare, just for the record.